Hello guys, last chapter for Physics 213, and this chapter is on oscillators and oscillations. An oscillator is an object or a system that undergoes a back and forth motion about an equilibrium point, okay? Pendulums are examples of oscillators. A mass hooked to a spring that's moving back and forth or up and down would be considered an oscillator. The most important type of oscillatory motion for this point for us is harmonic motion, or rather simple harmonic motion. And SHM, you'll see that abbreviation in the book quite a bit, is when an object oscillates in such a way as to create a smooth sinusoidal oscillation graph for position versus time. So you can see here that our position versus time graph is a sine curve, okay? And this is time. Position is on the vertical axis. From peak to peak, that's the period, the time it takes for the pattern to repeat. So if you think we go here, here, and here, the pattern starts to repeat again, okay? So, the line here, that's our equilibrium position. Notice we have the same distance of travel in the plus x direction and same magnitude of travel in the y direction. That's referred to as the amplitude, okay? Which is the maximum displacement from equilibrium. And the equilibrium line is the x equals 0 position, okay? Now, when we describe oscillatory motion, we're going to borrow some of the language and terms that we used when we talked about circular motion. Hint, they're related. Period, the time to complete one oscillation. You know, when we start over the pattern, when we were talking circular motion, it was the time to, you know, when we got back to the place where we began, one complete trip around the circle. Frequency is the number of cycles per second. So it turns out that frequency equals 1 over period, okay? Frequency equals 1 over period. And cycle, like radians, is a made-up unit, okay? It's not a true unit. It's just there to kind of advise us what we're looking at, but it's not a physical unit. As an object oscillates back and forth, its position is constantly changing. So its velocity is constantly changing. That means its speed's changing and or its position is changing. Now, for an object that's oscillating, its instantaneous velocity is 0 at the turning points, the furthest points from equilibrium. So if you're looking at that sine curve, it's the top of the peak or the bottom of the trough. That's where you're at your maximum displacement. X equals A or X equals minus A. The instantaneous velocity, it has its maximum at the 0 point. Okay, so when it's passing through equilibrium, that's when the velocity is going to be at its maximum. Velocity, of course, is positive if it's moving to the right, and negative if it's moving to the left. We would like to be able to relate position to time. So to do that, we need to know something about amplitude and period, and with that we can work out equations for position as a function of time and velocity as a function of time. So to understand simple harmonic motion, I first want us to look at a ball attached to the edge of a rotating disc, and we're going to concentrate on the motion of the shadow, okay? Now, if we have a ball here attached to a rotating disc and we shine light on it and we watch the shadow. If you watch the shadow, as this guy turns this way, the ball will move out and it'll reach a maximum shadow position. And then as it moves in toward here, it moves in toward equilibrium shadow position, and then it moves out to its maximum position in this direction. Then it moves back toward equilibrium and out. If you compared that to the motion of a mass attached to a spring going back and forth, guess what? They're going to match. And if you graph out the position of the shadow as a function of time, it's going to give you a sine curve. Remember just a little bit ago, I hinted at the fact that there's a relationship between circular motion and simple harmonic motion, and it's related through the motion of the shadow. Or you could say the X position of the ball on the turntable. Okay? So, turns out that the X position is given by the following equation. X is equal to R cosine of phi. Phi is the angle that it swept out. Okay? So, phi is called the phase of oscillation. For simple harmonic motion, the maximum displacement for the object from equilibrium is amplitude A. If I relate that to the ball on the disc, A is equal to R. So for a simple harmonic oscillator, okay, where x the displacement equals A at times t equals 0, so we're starting at the furthest point over here as it's going around, we can say that x as a function of time is equal to A cosine 2 pi t over the period. And it's most often written as A equals cosine 2 pi f times t. Just X that out, yeah. It's because I touched it. Now, 2 pi f, okay, can also be thought of as omega. Remember, omega is 2 pi over t, that's the angular speed, or 2 pi f, okay? So omega equals 2 pi f, or you could say it equals 2 pi over the period. So notice, angular speed, okay, has a role to play here. Now, note, when we're doing simple harmonic motion and we're talking about angles, you're going to be using the angles in terms of radians. So make sure that when you're doing these problems, your calculator is set correctly. Now, omega here, when we're talking about circular motion, we call it angular speed. Okay? Here in chapter 15, when we're looking at simple harmonic motion, it's usually referred to as angular frequency. So remember that theta final equals theta initial plus omega delta t. There is no angular acceleration here in simple harmonic motion, so you can figure out what angle a circle has swept out, or an object moving a circular pathway, by looking at that equation. Okay? Now, velocity, okay, let's rack your brain and remember a few things. Velocity is the first derivative as position as a function of time. So velocity is d dt of A cosine omega t. And guys, remember when you take the derivative of cosine, you get sine. Okay? So I get minus and you get the negative. So it's minus A omega sine omega t. So Vmax, the velocity at time 0, is, so Vmax is equal to pi f A, or 2 pi A over t, or omega A. Okay? So velocity as a function of time is equal to minus Vmax sine 2 pi t over the period, or minus velocity max sine omega t. All right, so let's look at page 393, and we're gonna, let's see, let me look and see what that is. So if it's a pretty picture that we need to look at. 393. Okay, guys. Here, we flip to the I don't think we have to worry about that. Okay, I'm going to look at problem 1 on page, at the end of the chapter. Okay? Let's zoom. Zoom in a little more. I swear, guys, I didn't undo the zoom. Okay, if we look at problem 1, it says an air track glider attached to a spring oscillates between 10 centimeter mark and the 60 centimeter mark on the track. So 10 minus 60, that's 50. So 50 divided by 2 is 25. Plus the 10, the equilibrium point is at 35 centimeters. The glider completes 10 oscillations in 33 seconds. We're asked the period, the frequency, the angular frequency, the amplitude, and the maximum speed of the glider. Okay? So, you guys look at that for a sec while I now start sliding you over. Okay, now the first thing we're asked is the period. Okay, that's the amount of time it takes to complete one oscillation. So it says 33 seconds to make 10 oscillations. So 33 seconds divided by 10 would give me 3.3 seconds as our period. B asks us the frequency. Frequency is just 1 over period, so it's going to be 1 over 3.3 seconds. So 1 divided by 3.3 is 0.303. Your book always takes things to 3 significant figures. You could either label this as cycles per second, or you'll see the unit hertz. Hertz means cycles per second. Okay? The next thing the problem asks us is omega. Omega is 2 pi f, so it's going to be 2 pi times 0.303 cycles per second, or hertz. So 0.303 times 2 times pi is 1.90 radians per second. Okay? A cycle and a radian are both made up units. It's just to help us remind us what we're dealing with. The next question asks us, what is the amplitude? Well, the amplitude is 25 centimeters. Now I got that because we were at 60 minus 10, and that's the total travel from one end to the other. That was 50 centimeters. And half of that is 25, and that would be our amplitude. F, oh, they don't have F, they have an E. It asks us the maximum speed of the maximum speed is equal to 2 pi f a. So I'm going to have 2 pi times 0.303 hertz, and A is 25 centimeters. So 2 times pi times 0.303 times 25. That says that Vmax is 47.6 centimeters per second. Now, here in chapter 15, we quite often use non-standardized units for speed because oscillating objects usually aren't moving that far, so it's quite common to see things in centimeters per second. So don't be thrown if you see that. Okay? Now, The other problem that I thought we might look at is problem 3. Let me see if we need to. This one's an easy one. Okay. If we look at problem 3, you can see it says, when a guitar string plays the note A, the string vibrates at 440 hertz. What is the period of the vibration? Okay. Now, we know the relationship between frequency and period is that frequency is equal to 1 over period. So period should equal 1 over frequency. So I've got 1 over 440 hertz. Okay? So the period is going to be small. 1 divided by 440 is equal to 2.27 times 10 to the minus 3 seconds. Not bad at all. Okay, guys, let's move on. Okay. Now, what we've been looking at so far is the case where the oscillating object is at x equals a at time equals 0. But we also have to have equations for when the object is not at x equals a at time equals 0. Okay? For that situation, we have the more generic equation, x at times t is equal to a cosine omega t plus phi 0. Velocity at times t is equal to minus omega a sine omega t plus phi 0. And a at times t is equals minus omega squared a cosine omega t plus phi 0. Phi 0 represents the starting position of oscillation. It tells us where we are at time 0. Okay, so let's look at these situations. Now, if we start out here, we're at a position to the right of equilibrium. We're on the positive x position, and we're headed left. Okay, we're moving in the counterclockwise direction. So we're moving, the shadow is moving left. So there's our phi 0. 3 over pi, remember we're dealing in radians, okay? So we're going to have a plus x and a minus v, all right? If I look over here, minus pi over 3, I'm in the same position, 1/2 a, but I'm traveling to the right, and I'm to the right, and I'm traveling to the right. So position is positive, and velocity is positive. So if you see a plus pi over 3, it tells you you're moving in the negative direction. If you see a negative pi over 3 is your phi 0, you know you're going in a positive direction. If you are at minus a, phi 0 is pi. Okay? And the velocity there is 0. Alright, scroll up for me. Now, here our graphs show you position is a function of time, velocity is a function of time. Notice here position is positive, velocity is negative. Here position is positive, velocity is positive. Here position is negative, velocity is 0. Turning points, okay, here, velocity is always 0. Okay. So a positive phi 0 indicates the motion is to the left, a negative phi 0 indicates the motion is to the right. Okay? Between 0 and plus 1/2 pi indicates a positive position to the right of the equilibrium and motion to the left. Negative pi to plus 1/2 pi indicates that we're at the equilibrium position and moving to the half. between negative pi and pi indicates a position to the left of equilibrium moving to the left. 0 to minus 1/2 pi indicates a position to the right of the equilibrium moving right. Minus 1/2 pi, we're at equilibrium, but the motion is to the right. And between minus 1/2 pi and minus pi indicates a position to the left of equilibrium moving to the right. Huh, that's a mouthful. Now, let's look at problem 5, okay, at the end of the chapter. Okay, let me see if I can blow this up just a little bit more. All right, guys, it says, what is the amplitude, frequency, and phase constant for the oscillation? Okay, if we look at the amplitude, okay, I'm just going to read this off to you. You can see the amplitude is 20 centimeters. Okay, just read that from the graph. To get the frequency, I'm going to need to first get the period. So if I look at this, let's see, there's one, this, if that's 0, if I come over here to there and down, that looks like 5 to a repeat. So I would say, yeah, I would say that the period here is 5, so the frequency is going to be 1/5. Okay? Because the period is to the point where the pattern repeats, and the pattern starts to repeat there at 5. So we've got a repeat of 5. Now, the last thing wants us to get the phase constant. To get the phase constant, I can use x at times t equals a sine omega t plus phi 0. Okay? Now, if I am using that equation, we know that the time is 0, and we know the amplitude is 20 centimeters. Okay? So I can, let's make that look more like a T. X at time t, looking at our graph, okay guys? And I moved that down, sorry guys. This runs much smoother in the classroom. X at time t is 10 centimeters. So I can go 10 centimeters is equal to 20 centimeters sine omega times 0 plus phi 0. So I get 1/2 is equal to the sine of phi 0. So phi 0 is the inverse sine of 1/2. So I'm going to make sure my calculator is in radians. Let's see, radians, mode 5, I'm in radians. So 0.5 inverse sine. I get phi 0 to be 0.524 radians. Okay. And there's our answer. Now you could have given the answer in terms of pi, but I'm not worried about that. You give me a decimal answer and I am going to be perfectly happy. All right? Now, we could also look at problem 6, but it's really the same problem. So I think one example is enough. So let's scoot back over. All right, now, a mass attached to a spring spring laid on its side on a frictionless surface, when stretched and released, will undergo simple harmonic motion. Notice I said frictionless surface. Okay, we're in physics fantasy land again. And it undergoes simple harmonic motion, just like the shadow of a ball attached to the edge of that rotating disc. So let's do stop and think 15.2 on page 397. So 15.2. Stop and think, come on. Where's my stop and think? There's 15.1, stop and think. Where did 15.2 go to? Here it is. All right. Okay, it says the figure shows 4 oscillators at time t0. Which one has a phase constant of pi over 4? Okay, well, we know that with a phase constant of pi over 4, which is less than 1/2 pi, it has to be on the positive side of equilibrium, and it has to be moving in the negative direction. Okay, so first off, I can knock out A and B because they're on the negative side of equilibrium. That limits us down to C and D. And since it's a positive phase constant, I know it has to be moving to the left. So our answer here is D. Okay? I don't have to do any calculations. I just have to know something about what the phase constants mean. All right, guys, let's move on. Okay, for a mass on a spring at x equals a and x equals minus a, all the energy of the system is the form of potential energy. Okay, because that's where the velocity has gone to 0. And remember, a spring force is a conservative force. Since it's a conservative force and we have no friction, we have conservation of mechanical energy. Okay, at x equals 0, all the energy is in the form of kinetic energy. And in between the maximums, x equals a and x equals minus a, and 0, we have a mix of energy in the system. Some of it's kinetic and some of it's potential. So for a spring mass system, when we look at calculating total mechanical energy, there are 3 ways that we can do it. Okay? We can say that the total mechanical energy is equal to 1/2 K, the spring constant, A squared, or 1/2 mv max squared, or in between, I can say that the mechanical energy is the sum of the spring potential energy, 1/2 kx squared, and the kinetic energy, 1/2 vx squared. Okay? So if we play with these equations a little bit, we can get some relationships. Namely, omega turns out is the square root of k over m, the spring constant over the mass. So notice the larger the the larger the mass, the smaller the angular frequency. And the smaller k, the smaller the angular frequency. Frequency is equal to 2 pi, the square root of k over m, and period is 2 pi square root of m over k. So notice the angular speed, the frequency, and the period all depend on the spring constant mass. And note, it doesn't depend on how far you pull the spring mass system away from equilibrium, which is one of those things that's a little bit mind-blowing. You think if you pull it out further, it should take longer to oscillate, but it doesn't. Okay? The acceleration at any point along the track is minus k over m times x, and the maximum acceleration has a magnitude of k over m times A. So let's look at problem 14. Okay? It says a block attached to a spring of unknown spring constant oscillates with a period of 2 seconds. So I'm going to go ahead and write that down. T, the period, is 2 seconds. Okay? It says, what is the period if the mass is doubled? So this is mass of m, and this is mass 2m. Well, let's think about equations here for a second. Okay, we know that T is equal to pi the square root of, let's see, it's m over k. Yeah, m over k. So I have 2 seconds equals 2 pi, the square root of m over k, and now I've doubled m. So if I double m, okay, I've taken this, I want to know 2 pi 2m over k, which I can pull the square root of 2 out. I have the square root of 2 times 2 pi, the square root of m over k, and I know that all of this is 2 seconds, so our period T2 is equal to the square root of 2 times 2 seconds. Now, it says, what if the mass is halved? Well, guys, we go through the same process. If we cut it in half, okay, T with 1/2 m is just going to be the square root of 1 over 2 times 2 seconds. Right? And then it asks us if the amplitude is doubled. Well, the amplitude's not part of the equation. It would have no effect. And then if the spring constant was doubled. So the spring constant, 2k, since k is on the bottom, I would get 1/2 times, square root of 1/2 times 2 seconds. Okay? Not complicated. You can do this. All right. Now, let's see. Let's see if I want, let's look at problem 15. Okay, guys? Now, let's read through the problem. It says a 200-gram air track glider is attached to a spring. The glider is pushed to 10 centimeters and released. The student with a stopwatch finds 10 oscillations, takes 12 seconds. What is the spring constant? Okay. So, we're told that our mass is 200 grams, that's 0.200 kilograms. And we're told that the glider makes 10 oscillations in 12 seconds. So I can say the frequency is 10 oscillations, 12 seconds. So 10 divided by 12, that's 0.833 hertz. And then we are asked, what's the spring constant? Now, if we look at this, okay, we're told, well, we know that frequency is equal to 1 over 2 pi, the square root of k over m. So if I'm solving for k, I get 2 pi times the frequency equals the square root of k over m. If I square both sides, I have 2 pi f quantity squared times m equals k. So if I plug into this, k then is going to equal 2 times pi times 0.833 quantity squared times the mass, 0.200 kilograms. So 2 times pi times 0.833 squared times 0.2. That's giving me 5.48, and that should be in, let's see, it should be newtons per meter. It's units of K. Okay. Not too bad. Should be able to do that. All right. Now, go ahead and switch over. Now, guys, these are just kind of plug and chug equations. You ought to be able to do them. Just kind of, looking at the equations and digging through what you need. Now, let's talk about a pendulum, okay? Pendulum is our other simple harmonic motion. Now, if we look at figure 14.9 here, we'll shrink down this image just a little so we can get the whole picture. Now, when we look at a pendulum, okay, and it's swinging, theta and S are negative on the left, they're positive on the right. We've got an arc length S here. And we think about this guy swinging, okay? Now, when we think about the pendulum swinging, the tangential component of the force that's pulling it back towards center is actually due to gravity. So in this case, our restorative force is gravity, or gravitational force. Now I'm going to draw here, guys. Okay? So I'm going to really exaggerate things. Here's my pendulum. There's my vertical. There's my angle theta. Sorry, it's not a straight line. You guys will have to forgive me. It's going to follow this arc, S. Now, if I draw in my axes, okay? And actually, I'm going to erase this and draw a better picture. Okay. Now, let's think about something following a circular pathway. Okay? This is our tangential axis. This is our radial axis. And our force due to gravity is here. So there's going to be a tangential component, and there's going to be a radial component. Okay? It is this tangential component of the force due to gravity that is the restorative force on that ball. Okay? So let's keep in mind that that's our restorative force. And we need a restorative force when we're seeing simple harmonic motion. All right? Now notice that force is in the negative direction. It's pulling it back toward equilibrium. This sucker is going to have an acceleration toward equilibrium. When it moves to the other side, the force would be in the positive direction. There would be an acceleration in the positive direction. So, let's look at the book's better picture than mine. But you know, you got to see me draw periodically. So notice here. That's okay, not a big deal. So there's our tension force, force due to gravity in the R direction, gravitational force, tangential gravitational force. Now, if that's the angle theta, that's the angle theta, and our tangential component is minus mg sine theta. Okay? Minus mg sine theta. So, we're going to be able to do an approximation here. Sine of theta equals theta in radians, which equals S over L for angles less than 10 degrees. So if we don't pull our pendulum back further than 10 degrees, okay, then I can say that the sine of theta is equal to S over L. So the force tangential is going to equal minus mgs over L. Okay? Getting acceleration, we know that acceleration equals force divided by mass. We get minus, acceleration equals minus g over L times s. S at times t is equal to a cosine omega t plus phi 0. Okay? Working through that, we can get omega is equal to 2 pi f, and it turns out for our pendulum, omega equals the square root of g over L, and I'm not going to do the math for you because you get bored with it. So as long as the angle is 10 degrees or below, I can approximate the angular frequency as the square root of g over L. So notice it's independent of the mass of the object on the pendulum. It only depends on the length of the pendulum and acceleration due to gravity. Now this is really neat. So that means that if you have a grandfathered clock and you're trying to adjust the time, if you've ever played with a grandfather clock, you actually adjust the length of the pendulum, not the weight of the pendulum. Now, if you are dealing with Big Ben, which doesn't have, it has a rigid pendulum, not a normal pendulum, they actually have to adjust the weight on that. But let's look at problem 24. Okay. It says a grandfather clock ticks each time the pendulum passes the lowest point. If the pendulum is modeled as a simple pendulum, okay, which is what we're looking at, how long must it be for the ticks to occur once a second? Now, let's think about this, okay? So, here's our equilibrium position. The ball comes through, it ticks here. It goes to here, and it comes back, and it ticks here. Goes to here, comes back, ticks here. So if it ticks at half a cycle. It's not a full cycle. So from here to here to here, okay, a full cycle, this is 1 second, that's from, let's see, if I take here to here is 1 second, here to here is 1 second, so that means that it's 2 seconds per cycle. So the frequency is actually 2 seconds. Okay? We know that omega is equal to 2 pi f, which in this case has to equal the square root of g over L. So I have 2 pi times 2 seconds equals the square root of g over L, or I have 4 pi quantity squared is equal to g over L. So L is equal to g divided by 4 pi squared. So I have 9.80 meters per second squared, over 4 pi, and that's hertz, which is cycles per second, okay, or just over seconds squared. So 9.8 divided by 4 squared, let's see, well, 4 squared times pi, no, 4 times pi squared, and then I go 1 over that times 9.80, and I get, hold on, 4 times pi squared okay, 1 over that times 9.8, and I get a length of the pendulum here of 0.062 meters. Okay, so that should be the length of my pendulum. Okay, problem's not bad, right? Now, let's also look at problem 25. Just to make sure we got 2 nice problems here. It says a 200-gram ball is tied to a string. It's pulled back to an angle of 8 degrees, so we're in the sweet zone, and is released to swing as a pendulum. A student with a stopwatch finds 10 oscillations in 12 seconds. Okay? It says, how long is the string? Okay, so our frequency is 10 oscillations in 12 seconds. And that means that 2 pi times 10 oscillations, 12 seconds, has to equal the square root of g over L. So I'm going to go ahead and multiply that through. My calculator. There it is. So 2 times pi times 10 divided by 12. I have 5.23598 over seconds equals the square root of 9.80 meters per second squared over L. And I've got to square that. So I have 2.288, hold on, 5.23598 squared. Okay, that looks better. 27.415 over second squared is equal to 9.80 meters per second squared over L. Solving for L, I get 0.357 meters. Okay, so pendulum problems should be real easy. Okay, guys, the last thing that we have to talk about here is a damped oscillator. Damped oscillations is an oscillation for which resistance, a dissipative force, is at play, and it removes energy from the system, and the oscillations decrease in amplitude with time until eventually the oscillator stops. Okay? How fast the oscillation stops depends on the shape of the object, the viscosity of the fluid that it's moving through. For something like a mass attached to a string moving on a surface, the frictional force is going to act as a dampening force. The angular frequency then of a damped oscillator is the square root of k over m minus b, the dampening constant, over 4m squared. Okay? So remember that a damped oscillator, the mechanical energy is not conserved. So let's look at figure 4.29. I mean, on page 4.29. should scroll down and it should be there. Okay, now here's what the graph of a damped oscillator looks like. Notice the amplitude starts out high and it decreases. This is the envelope of amplitude decay, and it's exponential. So x max is equal to a e to the minus bt over 2m. Now we didn't derive that equation. It would drive you crazy if I did. Okay, but notice that it dampens. So once you start a pendulum swinging, you know, just your standard pendulum, it's going to stop over time. It's going to keep getting slower. Now, a driven oscillation and resonance. A driven oscillator is one in which energy is being added with the same frequency as the oscillation of the object, and it increases the amplitude of the oscillation. The natural frequency at which something vibrates is called its resonance frequency. So when we want to drive an oscillation, we want the energy input frequency to match the resonance frequency. Okay, you guys can try this. Get a thin glass. Wine glasses work well here. And if you wet your finger and you rub it around the rim of the glass, if you rub it at the right speed, okay, with the right pressure, you can get the glass to start vibrating. It's really neat. Try it. You can make it sing. You've seen people go online, look it up, watch people bust a glass with sound frequency or with their voice singing the right noise. They're putting in a driving frequency that matches the frequency at which that glass wants to oscillate. And when you hit that and you pop in enough energy, the glass will shatter. Okay? I also want you guys to look at the Tacoma Narrows Bridge film. You can find that on YouTube. It's really easy. All right? And tuning forks. All right, guys, that is the end of the chapter. It's a short one, and it's the end of the semester. So good luck on test 4.